start out looking at 7.5. And the first part we're going to look at, it's called the sum and difference identities. So we've done unit circle. Okay, so let's take a look at that. So here's the circle. And when we do the unit circle, we usually put like an XY axis on it because the goal is to figure out coordinates. What kind of angles have we always worked with on this circle?
45, 90s.
So what are they all? Yeah. Yeah, they're all multiples of 30 and 60. And if you graph all the 30s and the 60s and the 45s, okay, so here's 45, here's 30, here's 60. And you can reflect those points into every quadrant. So 45 over here, one here, one here. And we've done all these before. When we deal with a 45-90 triangle, what's the coordinate for 45 degrees? That's going to be important to remember, yeah? Comma. Yes. Okay, so that's the coordinate for 45. How about for the 30? Remember, yeah?
The x value would be 1/2.
That would be for the 60.
The x value would be square root of 3 over 2.
Okay.
The y value.
And the y value is a half. And for the 60, it's flipped.
Yeah.
So not that we use the decimals a lot, but it's going to be kind of helpful to know what the decimals roughly are. Okay, so 1/2 is 0.5. Root 3 over 2. Does anybody remember what that roughly is as a decimal? Okay, so it's about 0.866. That's just going to help you to know that if you don't remember how to do unit circle trig, you can't do it in your head quick. Knowing that 0.866 is root 3 over 2, that'll be helpful. And root 2 over 2. Does anyone remember what that one is as a decimal? Yep.
May I say what the calculator says?
Sure.
0.7071.
Yep. So about 0.707. All right. That's pretty much all we need to do. All we need to know to do the 30s and the 60s. But if you look at those points, they are not equally spaced. You're missing this one, and you're missing that one in every quadrant. What angle do you think that first red dot is? Yep.
15.
So that's a 15. And how about the red dot up there? 75. So once we learn the sum and difference identities, we're going to be able to do the 15 and the 75 in every quadrant. But to do the 15 and the 75, you have to already know the 30s, 60s, and 45s. Okay? So that'll basically expand what we can do on the unit circle by, well, it'll expand it directly by 8 points. But once you learn the idea of how to do like 15, you might be able to figure out ways you can do other ones. Like you can do 7.5. Okay? You can always, if you know how to do something, you're always going to be able to do half of it. There's a formula to do that. So technically, you can keep expanding it to do as many as you want. You can do 45. You can do 22.5 because that's half of 45. But it gets hard if you want to pick one. Like let's say you want to do 37. I'm not sure how exactly you can get a 37. You know, let's see. It's not an easy way to get that one. But you can get lots of different ones. All right, so first of all, let's start by looking at that.
What was the decimal of root 2 over 2?
Root 2 over 2, 0.707. All right, so look at what's on the left and what's on the right. Sine of x plus 3 in parentheses compared to sine x plus sine 3. Do you think if I put what's on the left in y1 and what's on the right in y2, would they look the same? Well, what's happening in this one on the left? Yeah?
You're taking the sine of x plus 3. X plus 3 has like a separate value.
Okay, so can you explain to me what the plus 3 does?
So the plus, basically, if x was 5, instead of just doing sine of x and sine of 3, you're doing sine of 8. You're doing the combined sine.
So can you describe it as a transformation?
On a graph, up, down, left. The plus 3 would either move it left 3 units or up 3 units, and I'm guessing it's probably going to be left 3 units.
Okay. Does anyone agree or disagree with left 3? What do we think? Jacob, what do you think?
I think left 3.
Yeah, it moves it left 3. Okay, so we know that this is the basic sine function shifted left 3. What's happening in the second one? Yeah? What is it? It's not the same. That's a different transformation. Yeah?
It's not really moving it left or right. I'm pretty sure it just it's hard to describe.
Yeah.
Would it be a vertical transformation?
Mm-hmm. Which way?
Huh?
Which way?
Up.
Yes. That's a vertical shift. That's up, whatever the sine of 3 is. Okay, so that's a shift up. In general, shifting something left and shifting something up will not give you the same result. There might be a special circumstance where that happens, but in general, you can't just take the distributive property with a function and apply it like that. Okay? It's the same reason why when we talk about something like that, you definitely cannot say that at all. The distributive property does not work when you're trying to apply a function to something. Now, if it was multiplication, that's like with a square root, that's different. Okay? If you had the square root of 4x squared, that is the square root of 4 times the square root of x squared. But that only works because it's multiplication under the argument, not addition. So then what I want to do is figure out, well, what can we do with that? Right? If we want to somehow try to simplify that so it doesn't have this plus 3, and you can't distribute the word sine. That doesn't work at all. Well, what can you do? How can we handle that plus 3? This is an example of what we call a sine of a sum. Okay, there's a formula for that. There's formulas for adding 2 things and subtracting 2 things, for sine, cosine, and tangent, okay, for all of them. And that's what we're going to look at. We're not going to start out with the sine of a sum. We're going to start out with a cosine one. Which one do we start with? Difference. Okay, we're going to start with the cosine of a difference. Okay, this particular formula, I'm not going to prove to you. Okay, you can prove it. It's a little bit complicated to prove. Probably take 15 minutes, 20 minutes just to prove it. But once we have this formula, we can use it to figure out other ones quickly. Okay, so that's what I'm going to focus on. Okay, how can you use this one to figure out other ones quickly? Not figuring out this one. Okay, so that's the formula for the cosine of a difference. You can't just distribute the word cosine. But what you can do is this. When I pronounce it, I usually call that the first one. That's alpha. And I call that one the second one, okay, beta. And the reason I say first and second, is it helps me to kind of remember the formula. So it's cosine first, cosine second, plus sine first, sine second. That's the formula. All you have to do is fill in the first and the second. Okay, the alpha and the beta. Now, as we go through them, we're going to see some formulas where the cosines are grouped together on the left and the sines are grouped together on the right. We're also going to see some formulas where, I might not have it written down. Well, once we get to it, I'll write it down. But we're going to see some other formulas where you have a cosine and a sine next to each other and a cosine and a sine next to each other. So sometimes the cosines are together and the sines are together. Sometimes they're mixed. Cosines and sines are next to each other on one side and on the other side. That can be the hard part, just trying to remember which one is which. So again, the proof of that, it's on page 409, but definitely not something I want to go through. Okay, any questions just on the formula? Cosine first, cosine second, plus sine first, sine second. Another thing you can notice is when you have a difference and it's a cosine problem, it turns into addition. And as you would expect, when you have cosine and this is a sum, that's going to turn into a minus. Okay, we'll get to that. So let's see if we can figure out the exact value of cosine 15. What we're doing with the formula right now, it's okay. It's fine to figure out something numeric, but that's not really where this formula is really useful. This formula is more useful when you are doing more abstract things, like proofs. This is a simple example with numbers, just to show you how it works. So I want to figure out the exact answer of the cosine of 15. So I don't want a decimal. First thing I have to do is figure out how I can rewrite the number 15. But it has to be numbers that we know how to work with. So if you did like 25 and 10, well, 25 minus 10 is 15. But 25s and 10s are not on the unit circle. So you've got to rewrite your number in terms of 30s and 45s or 60s. Yep?
Okay, so cosine 45 minus 30.
Yes. If you have an angle that you're looking for and it's not on the unit circle, but you can rewrite it in terms of angles that are on the unit circle, you can figure it out. Now, if somebody said, well, what about 60 minus 45? Any two numbers that are multiples of 45 and 30 that subtract to give you 15, you can do it. Okay. All right. So now let's just apply the formula. Cosine, cosine, plus sine, sine. Okay. So let's fill that in. Cosine, cosine, plus sine, sine. And remember, first, second, first, second. So just fill in your angles. Okay, what's the first angle in this case?
45 degrees.
Yep, and the second? 30. Now we've got 4 problems we need to do, or 4 expressions we have to simplify, but they're all on the unit circle. Okay, if you don't remember cosine of 45 degrees, and you need to use the unit circle to figure it out, it's going to take you a while. Because you have to do the unit circle 4 times. So you think, okay, 45 degrees, cosine of 45 is 2 over 2, 2 over 2. Cosine is the x value, which is root 2 over 2. But if you've got to think that through for every one of them, it's going to take a while. That's where the decimal can come in handy. So if you don't remember that it's root 2 over 2, just type in the cosine of 45. Okay, make sure you're in degrees. Cosine 45, and you get 0.707. You have to now remember 0.707 is root 2 over 2. All right, so that's root 2 over 2. Now, cosine of 30. We already have the coordinate for 30, so it doesn't take that long to figure it out. What's the cosine of 30? Yep. It's square root 3 over 2. But if you didn't have the coordinate all done out and you couldn't remember it, you could type it in. You're going to get 0.866. And now you need to remember that that's root 3 over 2. Okay. Times 3 over 2 plus. How about the sine of 45? Based on what we have there, what's the sine of 45? Yep. Yep, it's the y value, which is square root 2 over 2. Times, and what's the y value for the coordinate for 30 degrees? 1/2. Yep. It actually doesn't take that long. If you quickly write those coordinates, then you have them. Or if you could just memorize them, even better. Okay. Now we're going to multiply together what we can. What do you get when you multiply those two together? Yep.
Square root of 6 over 4.
Square root of 6 over 4. And how about we multiply those two together? Yeah.
Square root of 2 over 3.
Square root 2 over
4.
4. And to add those two fractions together, you've got to make sure you have what?
On the denominator.
We already do. So we can just put them together. That is the exact answer for the cosine of 15. How could we check? Just make sure we did it right. Yeah, we just type it in. Let's type in the cosine of 15. Okay, we're going to get that decimal. Now let's type in what we got, see if it comes out the same. So type in square root of 6 plus square root of 2.
The x value for 15 degrees. Probably use it.
Yeah, that would be the x value for 15 degrees. Exactly the same thing. Well, I can't say most people, but at least I don't have the coordinates memorized for the 15 and 75. If I worked with them a lot, maybe I would, but I would have to figure it out like that each time. But it has lots of square root of 6, square root of 2s, and 4s. Sometimes it's plus in the numerator, sometimes it's minus, but it usually is some kind of variation with a root 2, a root 6, and a 4. That's how it usually works. So any question on how we got the cosine of 15? Okay. So I think the hardest thing can just be, how do you break up the number you want to work with into two angles? Like let's say I wanted you to do cosine of, well, let's do this one. What angle would this one be?
105.
105. So now you need to figure out a way you can break up 105. Can anybody think of two angles that are on the unit circle that you can subtract when you get 105? Yeah.
135 minus 30.
Perfect. Yeah. 135. That's a multiple of 45 and 30. And there might be other ways you could do it too, but that would work perfect. Now you'd go through and do the same problem again. The only difference is everywhere you had a 45, you're going to make it a 135. And what's the only difference between a 45 and a 135 in terms of the coordinate?
Here's the signs.
It's just the sign, right? The only difference is the x value becomes a negative. So essentially, that's almost the same problem. except the x value is a negative instead of a positive. But be very, very similar answer. Okay, I'm not going to go through and do that one, but is there any question on how we got 135 minus 30? Okay, let's try this one. So this is an identity. It's a verify. But it's not an identity where you really need to guess the direction you need to go in. It's a cosine, and it's a difference. So all you have to do is fill in what you have. That's like your alpha. And that's your beta. So remember the formula. Cosine, cosine. Sine, sine. And someone remind me, what goes between the two? Right. When you're dealing with a cosine, what you put here is the opposite of what's inside there. Okay. What am I going to fill in for my my first angle? Yeah.
Pi over 2.
Pi over 2. And what am I filling in for my second angle?
Theta.
Theta. So you're not going to be able to do much with the theta. That's a variable. The only thing you can work with is cosine of 90, or cosine pi over 2. Now, this is one we should be able to think through it on the unit circle. Kind of just said it, but where's pi over 2? Yeah? It's at 90, and what's the coordinate when you're at 90?
0, 1.
0, 1. Okay. Cosine is which letter in the coordinate?
X.
It's the x. So what's the cosine of 90?
0.
0 times. You can't do anything with cosine theta because that's a variable. You don't know what theta is.
But you can do this on the other hand. Because it's 0, you can cancel everything out.
Yep,
Because
everything's going to cancel there in the next step. Yep, exactly. What about the sine of 90?
It's 1.
It's 1 because the sine is the y value and the y value is a 1. Okay, so now I was going to mention here when you multiply 0 times anything, it cancels out. So now all you're left with is 1 times the sine. Well, what's 1 times sine? Sine. So we just proved that this equals that. Okay? That's why I said I think you'll find the proof today a little easier than the kind of proofs we did before. That's pretty much how it works every time. You can usually do it in like 2 steps.
So since theta is a variable, if it was like pi over 2 minus pi over 4, would it equal sine of pi over 4?
Yes. Yeah. Yeah. We usually don't use it with an exact value, but yeah, that should work perfect. Yeah. And if you look at this angle and this angle, just compare these two numbers. Pi over 2 minus theta and theta. If you think of it in degrees, what kind of angles are these? Pi over 2 minus an angle, and then the angle.
Oh, complementary.
Those are complementary. Okay, these are always complementary angles. And we had a theorem that said if you have co-functions of 2 angles that are complementary, they're always equal to each other. That's a theorem we learned earlier in chapter 6. So it's kind of just looking at that theorem a different way. Yep. Yeah, that's a good point. All right, let's try this one. So this is saying the cosine of pi minus theta is equal to the negative cosine of theta. Okay. Which side do you think we're going to work with?
Left.
Yep, I'm going to work with the left. And I would classify this as a cosine difference problem. There's really 6 different types you're going to have. Cosine sum difference, sine sum indifference, tangent sum indifference. Okay, this is cosine difference. All right. Cosine, cosine. Sine, sine. What goes between the two terms? Yeah. It's always the opposite of what you have right here. Add. If it was added, then it would be a minus. We haven't learned that yet, but that's the pattern. What do we fill in for our first angle? Pi. Second angle? Theta. Pi. Theta. Okay, you're not going to be able to do anything with the theta, but you can with the pi. Where's pi on the circle? It's at 180. What's the coordinate when you're at 180? Negative 1, 0. Good. Now we should be able to figure this out. Cosine is the x value. What's the x value for 180?
It's negative 1,
Negative 1.
and the sine value is 0.
And the sine value is what?
It's 0,
The sine is 0 because it's the y.
which drops everything on the right side of the equation to 0.
Yep. So that's 0 times sine, which is gone. And what's negative 1 times cosine?
Negative cosine.
Negative cosine. So that proves that cosine of 180 minus theta is the negative cosine of theta. So this has something to do with supplementary angles, specifically for cosine. I don't know any real theorem that that's formalized as. This last one is basically the complementary angle theorem. But this one, I don't think it has any. Any question on that one? All right. So if we can do cosine of a difference, we should be able to do cosine of a sum. Okay. Two things are going to come up here that we mentioned before. We talked about when you have a negative inside here, what can happen. Does anybody remember when you have a cosine function, what you can do with the negative that's in front of that x? We didn't talk about this a lot, so sometimes people don't remember it. Yeah?
Like you just flip it to be from negative to positive, or you take like that's the value of it.
Not quite. Yeah.
Can you put the negative in front of like the cosine?
Yes. Sorry, it's kind of hard to. Oh no, sorry. For sine, you can do that. For cosine, the negative goes away. Okay, the negative can just go away. So, for example, if you do the cosine of negative 15, or you do the cosine of positive 15, the negative doesn't make a difference.
Like its absolute value.
No, because it could come out negative, like the cosine of negative 120. That is a negative answer. And the cosine of 120, still a negative answer.
No, but like it's it doesn't matter where you put it in. Like you.
So putting a negative in front of the argument in a cosine function doesn't affect it at all. And that's because if you graph cosine x and cosine negative x, what is that negative doing?
Just reflecting
It's a reflection over which axis?
the x. Right?
It's horizontal. Horizontal is
So you check the y.
the y. And cosine, let me just graph this in a better window. Cosine is symmetrical over the y-axis. If you flip it over the y-axis, you don't see a difference between the two. That's why cosine x and cosine negative x are the same thing. Okay? They're exactly the same thing. So with cosine, you can get rid of a negative in the argument, With sine, you cannot get rid of it. But what you can do, and this is what I accidentally said yes to at the beginning, you can move it in front. Okay, with sine, you can move it in front. And you could verify that. You could graph what's on the left in y1, what's on the right in y2, and you could see it. But the important thing is any question on how you can get rid of a negative inside the argument, whether it's sine or cosine. Because we're going to have to do that next. Okay. So, I want to figure out the formula for cosine of a sum. What's the cosine formula we know how to do right now? Or what's the situation we know how to deal with? If it's cosine of a difference, then we need to figure out how to rewrite this as a difference and use what we already know to figure that out. So how could you write alpha plus beta as a difference? Yep. Alpha minus negative beta. Exactly. So think of that as the first thing you're going to plug in. And think of that as the second. Is there any question why alpha minus negative beta is the same as alpha plus beta? Let's plug all of that into the formula we already know and see what happens. Okay, can somebody tell me how to plug that into the cosine difference formula? Tell me everything you're going to write out. Yeah? Cosine of what?
Oh, of alpha.
Mm-hmm.
Cosine
Negative beta.
Plus.
Yep.
Sine of alpha.
Sine alpha. Yep.
Times the sine of negative beta.
Now, we don't want those negatives in. Okay, we want to get rid of them. How can I get rid of that negative? Yeah.
You can just like for the cosine, the rule is that like the negative just doesn't matter. That's gonna like be the same whether it's negative beta, positive beta.
Yeah,
So
for
you
the
can just
for the negative there, we just get rid of it.
yeah.
Doesn't make a difference. Now, how about that negative? How can I get rid of that one? Yeah.
Move the negative in front of the sign.
Right, you can move the negative in front. Okay, so instead of being sine of negative x, we can make it negative sine x. Okay, same thing here. Move the negative in front, that's going to turn into a minus sine alpha, sine beta. And that is the formula for the cosine of a sum. It's cosine, cosine, sine, sine, and since it's a sum, we put a minus between them. Okay, any question on that formula? Now, technically, anything you can do as a minus, you can do as a plus. You don't technically need that formula to figure anything out. Anything I can figure out with that, I could have figured out with the first formula I gave you. But sometimes mentally, that formula helps to figure out something like this because it makes just more natural sense. So when I think of writing 75 as 30s and 45s, I naturally think of addition. That's what I go to right away. You could think of it as subtraction, but I think addition is more natural. How can you write 75 as a sum of two angles? We already know how to work with, yeah.
60 degrees
90 degrees. No. This is a sum. Sum. Oh, sum. It's 60 plus 15.
Well, a 15 is going to be hard to work with because we don't know a 15 off the top of our head.
45 plus 30.
45 plus 30, yeah. You always want to go back to 45s and 30s because in theory we have all those memorized, so we can do them pretty quick. Okay, now, can someone take that and expand out the cosine sum for me using 45 and 30? Yep.
Cosine 45, cosine 30.
Cosine 45, cosine 30. Now the real important piece,
Minus sine 45, sine 30.
5, 30. And we've done all those before. I think we did them all in the first problem. What's the cosine of 45?
Square root 2 over 2.
It's the x value of root 2 over 2 of cosine of the 45-degree angle. When you do a 30, what's the x value?
Root 3 over 2.
It's root 3 over 2. And the way I remembered that is I just imagined the triangle in my head. The long side is on the x for the 30, and that's the long side. What about sine 45? Root 2 over 2. And the sine of 30, now you're looking at the short side, 1/2. It's almost the same answer as the first problem, except it's a minus instead of a plus. So root 6 minus root 2 over 4. I think we had a plus in the first one, didn't we? What was the first?
No, it wasn't plus.
Was it a plus?
That would make sense though, because 15. That's like they're swapping the 15 and 75 probably the same coordinates, right?
Just switched, yeah.
Yeah.
The x and the y just switch places. Yep. So any question on how we got the cosine 75? All right. How about if I did, again, just thinking about how you would split it up. Let's do cosine. What would that one be? That's a 165. It's 15 degrees before 180. How could you split up 165?
Use the same values we already found.
Well, it's probably it's gonna end up being lots of root 3 over 2s and 1/2s and stuff like that. But how would you break up the 165? Yeah?
You do 135 plus 30.
You could do cosine 135 plus 30. Yep. If you wanted to think of it as a sum. How could you think of 165 as a difference? Yeah?
You can do 180 minus 15.
We want to stay away from using the 15 because unless you know the 15 off the top of your head, now you're going to have to figure out the 15 to do that. 45s and 30s we should know right off the top of our head. Yep.
Can we use like, can we use 210?
210 is a multiple of 30. If you can figure out something with 210, sure.
Do 210 minus 45.
Multiple of 30, multiple of 45, multiple of 30, perfect. So whichever way you want to think about this problem, you can do it either way. Okay. Any question on that? And again, expect to see lots of root 3 over 2s, root 2 over 2s, and 1/2. Those are the three numbers that are going to keep popping up. As long as you stick with sines and cosines. Tangents, it's a little different. All right, so here, I wrote that we know this. How do we know that? Well, I think we proved that earlier. Sine of theta equals the cosine of pi over 2 minus theta. Okay, we didn't prove exactly that. We proved it the other way around. But we could have proved that one exactly the way we proved this one. And technically, we kind of already know this because these are co-functions. Sine, cosine. And what kind of angles are these? Theta and pi over 2 minus theta. They're complementary. These are co-functions of complementary angles, so of course they're equal. That's a theorem. Knowing this complementary angle theorem, we can figure out a formula for the sine of a sum.
That's too much.
This too much?
The complementary adds up to 90 degrees, right?
Yes, complementary angles add up to 90 degrees. Anyone have a thought on how we can figure out the formula for sine of a sum? It's going to start by manipulating this sine alpha plus beta somehow. If I can, I would like to write alpha plus beta maybe a different way. Anyone have a thought? Yeah?
Can you do like sine and alpha minus negative beta? Can you do that, or do you want to just?
Well, you could. The thing is, we only have formulas right now for cosine. We have the cosine sum and the cosine difference. So somehow we have to get rid of sine because we don't know how to work with sine. I mean, we will after we figure out this formula. But for now, we've got to convert sine into cosine. And that's exactly what this top one does. It converts sine into cosine. So let's start by writing cosine. And see if we can figure out something we could put here. You basically have it up above. Think of this whole box as theta. And apply what you have right above it. Yeah?
Well, I was gonna say you could do pi over 2 since sine and cosine are
Yeah, cosine of
complementary functions.
pi over 2 minus what?
Theta.
Alpha plus beta.
Alpha plus beta.
So the cosine is the pi over 2 minus the angle. That's your angle. Well, in this case, that's my angle. So take that and fill alpha plus beta in for my angle. Pi over 2 minus, and actually I should put parentheses. Is there any question on how I got that part? It's pi over 2 minus the angle. I don't care what you want to call the angle. Alpha plus beta, triangle, whatever you have there. Just put it after a minus sign. And that's how you change it to cosine. Okay, now what I would do, we've got a minus in front of those parentheses. So what could we do with that? Yep, we could distribute that. So minus that. Minus beta. Now, what you have there is basically cosine of a difference. If you don't see it, I'll make it obvious. That's your first angle. That's your second angle. So now, use the cosine difference formula to simplify that, and you'll get the answer. Okay, so let's write it out. Cosine, cosine, sine, sine. And what What goes in between the two when we have cosine of a difference?
Addition.
Addition. Okay. What's going to go in my first parenthesis?
Pi over 2 minus alpha.
Pi over 2 minus alpha. And my second one?
Beta.
Beta, not a lot we're going to be able to do with just the beta. What's going to go in my first one over here?
Pi over 2 minus alpha.
Pi over 2 minus alpha. And my second one?
Beta.
Beta. Now, look at what you have right here. Cosine of pi over 2 minus alpha. That can be simplified. What does it say up above that the cosine of pi over 2 minus an angle equals? Yep.
You can have cosine of pi over 2 plus the cosine of alpha, I'm pretty sure.
Not quite. Yeah? That's sine. Whenever you have 90 minus an angle, you can just change it to the cofunction. Pi over 2 minus your angle is just the sine. Cosine beta, well, just cosine beta. Now, likewise, we have sine of 90 minus an angle. The sine of 90 minus something is the same as the what?
Cofunction.
The cofunction, which is?
Cosine.
Cosine. And that is the formula for the sine of a sum. Okay. A couple important differences here. We had a sum in the parentheses. We have a sum in the problem. Also, the trig functions are not grouped. By grouped, I mean we used to have all the cosines together on the left, all the sines together on the right. Now they're mixed. Sine, cosine, cosine, sine. So sine of the first, cosine of the second, plus cosine of the first, sine of the second. So that's where it gets a little hard, because they're all kind of similar. If you forget one of them, you can always figure it out again from scratch. And that's kind of annoying to have to do it, but you can. Okay, that's the cosine of a sum. A sine of a sum. What do you think the sine of a difference would be? That's the last sine one we haven't done. There's only one thing there that would change. Yeah?
So when sine has like the negative thing inside it, it moves to like the front, so it'd be like negative sine.
So there's one thing that would change in that box. And it would turn into
the minus, plus and minus.
the plus would change to a minus. Yep. So the sine of a difference is sine of the first, cosine of the second, and it's a difference, so then you'd have a minus. Cosine of the first, sine of the second. And technically, now that I've shown you all the sine and the cosine ones, you should be able to figure out this one. There's a shortcut for it, but I don't need to tell you the shortcut. Because what do we know about tangent? Yeah? It's sine over cosine. So even though that's a long way to do it, you could figure out the tangent of 15 degrees by finding the sine of 15 degrees, which we've already done, the cosine of 15 degrees, which we might have done, I don't know if we did that one, and then dividing the two. Okay, I am going to give you a formula for how to do the tangent quicker. But honestly, off the top of my head, I never remember exactly what it is. I know it has a 1 plus and then a 1 minus, and it has like a tangent times tangent, but I always have to look up what the formula is. But if somebody said, well, you need to figure it out without looking it up, then I'd say, okay, I can do it this way because I know what these formulas are. And if I don't, I know how to figure them out if I have to from scratch. So with the sine, sum, and difference, you can do all the same things we did with cosine. You could find the sine of 15, cosine 75, just a little bit different formula. All right, I'm going to give you the tangent ones, and then we'll talk more about where the tangent one comes from tomorrow. But for today, I just want to give it to you. If you took the sine and divided by the cosine, and you simplified the formula, that is exactly what you would get. And I do remember how to prove it, but I'm just not going to go through it right now. But my hope is that you could figure out, knowing the plus version, what the minus version would be. What do you think the numerator would be when you have to do tangent of a difference? Yeah?
Does that negative sign turn to a positive sign?
So what do you think would be in the top?
And the negative would be in the top. Or
All right, so read the whole top to me. What do you think it would be?
Tangent of alpha minus tangent of beta.
Yes. So it'd be tangent of alpha minus tangent of beta. And anybody think they know what the bottom would be for this one? Yep.
The 1 plus all those?
Yep, 1 plus the product. So it's not that they're long formulas, it's that they're so similar to other formulas, it's kind of hard to remember what's the plus and what's the minus. If you ever need these formulas, I would let you look those up, or I would give them to you as a reference. So don't worry about memorizing the tangent ones. The sine and cosine ones, yes, you need to know those. But don't spend time trying to memorize these, because you really don't need them. You could do anything with tangent just doing sine over cosine. It takes longer, but you can do it. Okay. All right, so those are the sum and difference. And these next couple groups, we're going to start a little today. We're going to review them again tomorrow. What we don't like to have when we're doing a trig problem, we don't like to have other things inside the parenthesis. We don't like negatives in there. We don't like other numbers in there. We just want to have a single letter. Okay, that's always kind of the goal. Well, if you have a 2 inside the parentheses, what kind of transformation is that?
Stretch.
What kind of stretch? Yeah.
Horizontal.
Horizontal. And this technically would be when you make a 2, it compresses it. So it's a stretch by 1/2, or you could say compressed by 2. Now, what kind of transformation is the one on the right? Yeah. It's a vertical stretch. In general, a horizontal and a vertical stretch are not equivalent. Maybe you could find a special graph where they are, but in general, they're not. So what can we do to get rid of a 2 in front of that x? So what do we do? So let's take sine 2x. This will be example 4. So I'm going to say rewrite sine 2x in terms of sine x. We could do this with cosine 2x. We can do it with tangent 2x. We can do it with all of them. I'm just going to do it with sine. So how could you rewrite 2x? Think about what would you have had that would have given you 2x? Yes.
X plus X.
Let's think of it as x plus x. Because now, that's the sign of a sum. We just came up with a formula for that. Can someone just give me, you don't have to fill in yet, but just give me the template when you have sign of a sum. Is it like cosine, cosine, sine, sine? Is it what is it? Yep.
Sine of x.
So sine, yep,
Times cosine.
cosine. Okay. And when you're dealing with a sine, you copy down the same thing you have in the parentheses. When you're dealing with a cosine, you have to switch it. So sine times cosine, and then what comes next? Cosine. I said I wasn't going to fill it in yet. Okay. And now fill in your angle. 1, 2, 1, 2. What's my first angle? My second angle? And then first angle, second angle. So I have sine times cosine plus cosine times sine. What does that simplify to? Yeah.
Is it 2 sine x plus 2 cosine x?
Not quite.
Times 2 cosine.
Well, we go right here.
I thought it was plus 2.
Well, this is like having x times y plus y times x.
Yes.
Same thing. Yeah.
Is it times 2 cosine x?
So read the whole thing.
2 sine x times 2 cosine x.
It is a times, but not quite what you said. But what's y times x the same as? X times y. So what's x times y plus x times y? 2xy. You have 2 of the xy's. So
So it's just cosine x.
2 of the sine cosines.
Yes.
That's how you get rid of a 2 inside the argument for sine. You turn 2 sine 2x turns into 2 sine cosine. Now, let's just try one more. Let's try cosine 2x. I don't want to have the 2 here. So how could you rewrite the 2x?
X plus X.
X plus x. Now that's the cosine of a sum. What's the template when we're doing cosine of a sum? Yep. Cosine times cosine. You switch the sign. Sine times sine. First angle. Second angle. Okay. What's cosine x times cosine x? No, not 2 cosine x. Yep. Cosine squared x. And what's sine x times sine x?
Sine squared X.
Sine squared x. That is how you get rid of a 2 when you have a cosine. It has to become cosine squared minus sine squared. Right, I'm not going to do tangent 2x. Let me write these all down. So we already did that. That's what we just proved. Okay, these are called double angle identities. Here's the first one. 2 sine cosine. Now, here's the second one. Is that the version that we wrote? Cosine squared minus sine squared? That's the one we wrote? Does that look similar? It's not, but does it look similar to something we've done?
The equals 1 thing.
What
the,
equals 1?
The identities.
Pythagorean thing.
Yeah, what is it?
Cosine squared plus sine squared equals 1.
Yeah, it's not that, but it looks similar to that. Now, if you use this, what is cosine squared equal to?
1 minus sine squared.
That's just a rewriting of a Pythagorean identity we have. Now, if you took this and you filled it in right here, you would have 1 minus sine squared minus sine squared. What would that turn into? It's like 1 minus x minus x.
1 minus 2x.
That's 1 minus 2x. So this would turn into 1 minus
2 sine squared.
It's just a different way of writing the same thing. And if you instead got sine squared by itself, you could even write it a third way. I generally don't have all these memorized. I remember the first one. And then if I have to figure out the second or the third one, I can. But it's not something I memorize. Okay, and the tangent one, I never remember what that is. Again, I never remember tangent because if I really have to figure out tangent, I can figure out the sine, and I can figure out the cosine, and then divide the two. It's going to take me longer to do it, but I can do it without that. So again, if you needed the tangent one, I would give you that one, but you need to know the sine one. So sine 2x is 2 sine cosine, and cosine 2x is cosine squared x minus sine squared x. Okay, so these are called double angle identities. It takes a trig function that has a 2, and it gets rid of the 2. Okay, does everybody have those? Yeah. Okay, we're going to try one with a double angle. That's going to be the last thing we look at. Just make it up. Let's do this example. I want to simplify sine 3x. Okay. Did I give you guys any triple angle identity formulas? I don't even know what triple angle identities are. They probably exist. I don't know what they are. So I want you to think of how we can rewrite 3x in terms of something we already know.
2x plus 1.
Exactly. 2x plus 1x. Now this is sine of a what? Sum. So use the sine sum formula on them and see what happens. What's the template when you're doing sine? Do we group them or do we mix them?
Mix them.
Mix them. Sine, cosine. Cosine, sine. What symbol goes between?
Plus.
Yep. We put a plus because it's sine.
The sine moves it back.
And what's our first angle?
2x.
What's our second angle?
X.
First angle
2x.
and second angle.
X.
That and that are fine. They don't have any numbers in front of the x's. This and this are not fine. But now, the biggest number in front of an x is a what? It's not a 3 anymore.
2.
Now it's a 2.
You need
And
square.
we have formulas to simplify those on the other page. What is sine 2x? What does that turn into?
Sine x plus x.
So I don't want to derive it all over again. I want the final result of sine 2x. Yep.
It's like 2 sine x and then cosine.
Yep. Yep. Done. So that's how you could derive it again from scratch. But once we know it, we're just going to use it. So that one's done. That one's done, which I can combine it and make it cosine squared in a second. What's cosine 2x? Just give me the top one. I don't care which one, but I want the top one. Yep.
It's I'm pretty sure it was cosine squared x minus sine squared x.
Times sine x. And I mean, where you stop with that, I mean, it depends what they want you to do. You could distribute this out and say 2 sine x cosine squared x. I'm just going to leave it like that. Because if the goal is just to get rid of the numbers inside the argument, you've done that. There's no numbers inside any of the arguments. They're all just x's now. So that's an example of how you apply a double angle identity. Now, the higher this number gets, the worse the problem gets. Okay, if you have like a 5x or a 6x or a 7x, then you have to keep splitting it multiple times. With a 3, it's not that bad. You got to do it basically one time, and that's all the work. But when it gets higher than a 3, it gets longer. Any question on that?
Would it be easier to have it so there was, when splitting it down, would it be easier to have like, you subtract one of the x's out of it and have it like,
yeah, so
replace it, or like just kind of split it in a certain way?
kind of depends on the problem. Like if you asked me now to do sine 6x, well, now that I know 3x, if I could make like a reference sheet of ones I figured out in the past and just use that on a test, since I know 3x, I would do it like this. 3x plus 3x, because I already know 3x right there. So the way I would break it up, it kind of depends on what I already know.
You could also just like have the entire thing in parentheses there and then just add 2 in front of it.
Yeah, so yeah, there's different ways to do it. A lot of people might do like 5x and 1x. But since I know 3x from the last problem, that's why I would do it that way.
But if you don't know any of the other ones, which the idea, would it be better to
take one off each time? Yeah. The idea would take one off each time. That's how I would go about doing it. If it was a big one, yeah. Okay, so those are the questions for tonight. So it's 1 through 5, 9 through 11, and 17. Okay, and if you had trouble with any of the identities, we'll go back over some of them again tomorrow. We'll do some more.
That should be.